let's have a look at combinatorics. Suppose you have 5 objects, A, B, C, D, E, and you wish to choose 3. So we've got 3 slots. How many different ways are there of choosing 3 objects out of 5? Well, we could choose A, B, C. We could also choose A, B, D, A, B, E, A, C, D, A, C, E, A, D, E, B, C, D, B, C, E, B, D, E, C, D, E. There's going to be 10 different ways. So now let's generalize. Given n objects, we wish to choose R out of them. So we've got a bag containing these n objects, 1, 2, etc. And we've got R slots. So how many objects can we place in the first slot? Or we could pick any one out of the bag and place it there. So we can place n objects in here. And then once we've placed an object here, how many can we place here? Well, we've taken one out, so there's still n-1 in there. So we could place any of those. In there, and so on. So this is going to be n minus, this was n minus 0, and there's r of them, so it's going to be n minus r minus 1. 0 to r minus 1 is the same as 1 to r, which is our objects. So for each positioning here, we have, for each of these n choices, we have n minus 1 choices here. And for each of those n times n minus 1 possibilities, we've got n minus 2, and so on. So the total answer is n times n minus 1 times n minus 2 times ... n minus r minus 1 is the same as n minus r plus 1. And we could write this using factorials, because this is equal to 1 times which is just n factorial over r n minus r factorial. Does that make sense? This just cancels with this, leaving us all we had there. Now if we quickly look back to our original problem with A, B, C, D, E and 3 slots, this system which we've just calculated, we could be putting 1 in here, 2 in here, 3 in here, or we could be putting 2 in here, 1 in here, 3 in here. And there's more ways of doing this, but they're all going to come out as different from one another. So this big number we end up with is full of duplicates. In fact, there's going to be 6 here, because how many ways are there of fitting 1, 2 and 3 into 3 boxes? Well, the 1 can go in 3 boxes, and this leaves 2 boxes, and the 2 can go into either of them, leaving 1 box for the 3 to go into. So that would be 3 factorial. But we have R slots, so there's R factorial duplicates. So therefore we have to divide this by R factorial. So if the order is important, i.e. 1, 2, 3 is different from 3, 2, 1, then that's called a permutation. So there are n factorial over n minus r factorial permutations. And n factorial over r factorial combinations. And this is equal to n choose R. What happens if we know 5 choose 3 and we know 5 choose 4? Can we figure out 6 choose 4? Just using these. So we've got 6 objects in the bag, and we've got 4 slots. And we want to know how many combinations we can make given 4 slots and 6 numbers to put them in. So there's going to be combinations containing a 6 and combinations not containing a 6. So combinations containing a 6, I might as well put it in here, and that gives us 3 further slots to work with. And there's also combinations not containing a 6. So if a combination doesn't contain a 6, then it's only using the numbers 1, 2, 3, 4, 5, and this is just fitting 5 objects into 4 slots. So that's just 5 choose 4. If it does contain the 6, then there's 5 remaining objects in the bag, and we have to fit them into 3 slots. So this is 5 choose 3. So actually, we add those together and we get six choose 4. So this lets us build. Let's start somewhere simple. Let's start with 2 objects. So 2 objects, choose 0 objects. How many ways are there? Well, there's only one way. You choose 0 objects. 2 objects, choosing 1 object. Well, you could choose the first or the second. So there's 2, choose 1. This was 2, choose 0. And 2 objects, choosing both of them. There's only one way to choose both of them. 2, choose 2. So given this, can we now get the line for 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3? 3 choose 0 is obviously 1. There's only one way of choosing 0 objects, and there's only one way of choosing 3 objects. And then we can just use this. 2 choose 0 is 1, 2 choose 1 is 2, so 1 and 2 is 3. That and that again is 3. So we can build. The next level will be 1, 4, 6, 4, 1. And we can go back up as well. The next level up would just be 1, 1, and then 1. And this would be given 1 object, choose 0 objects, given 1 object, choose 1 object. And from 0 objects, choose 0 objects. There's only one way of doing that, etc. And this is called Pascal's triangle. What happens if we expand out u plus v squared? Well, you can do that geometrically. There's u, there's v. So it's u times u, u times v, v times u, v times v. Which is u squared plus 2uv plus v squared. And you could notice that's 1u squared, 2uv, 1v squared, which is 1, 2, 1 here. So you might expect u plus v cubed to equal u cubed 1331 plus 3 u squared v plus 3 uv squared plus v cubed. And of course that is correct. 1331, etc. So Pascal's triangle gives us a simple way to write u plus v to the power of n for any n. Let's just have a look at why this is true. So u plus v cubed, well, we're just taking u plus v squared and we're multiplying it by u plus v. So we've got u plus v times this thing, u plus uv plus vu plus vv. And you had 4 things here, you're now going to get 8 things because it's now just u times each of these plus v times each of these. So you've got u, I'll put a dot u times uu plus u times uv plus u times vu plus u times vv, and now the same with v. And you can extract, if you like, 3u squared v. Where are they? We've got 2u's and 1v. There's one of them. There's another of them. And there's the third one. So you can see that u plus v to the power of n is just going to be a bunch of these objects, going to be some amount of u to the n plus some amount of u to the n minus 1 v plus da 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 plus some amount of v to the n. So these endpoints are just going to be 1. There's only one case where we have all u's and one case where we have all v's. Now for this one, we've got to look through all our permutations, and we're only interested in those permutations that have a single v and all the others are u's. So if we've got n slots, then our v could be here, or it could be here, or it could be anywhere. There's n different places it could be. What about the next one? So let's insert this term here, rather than pointing an arrow to nothing in particular. That's going to be something we don't know yet, times u to the n minus 2 times v squared plus all the way up to 1 times v to the n. Obviously it has to be symmetrical with u and v because you could just swap them. Okay, so we're after every block with 2 v's in it. So how many blocks have 2 v's in there? Well, how many ways are there of choosing 2 things out of n things? It's got to be n choose 2. And here we could just be writing n choose 1, because we're choosing 1 v out of n blocks. Does that make sense? So we could even rewrite the ones. So let's write it out in full. So n choose 0 u to the n v to the 0 plus da da da. So we could write that in sigma notation if we like, just to show off. Sum from 0 to n choose I, u to the n minus I, v to the I. Another thing to notice is that with u plus v squared, how many terms do we have? 4 terms. With u plus v cubed, we've now got 8 terms. By terms, I'm talking about the permutations, the UUU, UVU, UUV. How many possible permutations of length 3 involving u and v are there? And the answer is 8. And for u plus v to the 4, it's just going to be 16 because you're doing u plus v times this block of 8, which is u times the block of 8 plus v times the block of 8. So it doubles every time. So we know that our 1 plus 3 plus 3 plus 1 make 8, and the next line 1, 4, 6, 4, 1 makes 16. So it's just worth noticing that if you add all the elements in Pascal's triangle, you get 8 here, 16 here, 4 here, then 2, then 1, etc. So it doubles every time. If we write out a couple more, now, for example, what would, if we wanted to add up all of these elements here, is there a simple way to do it? Well, 1 plus 4 is the same as 1 plus 4 giving us 5. So 1 plus 4 plus 10 is the same as 5 and 10, which is 15. So 1 plus 4 plus 10 plus 20 is the same as that of 15 plus the 20. So whatever length thing we draw here, the sum of those is just the element back here. And that's called the hockey stick lemma because this shape looks like a hockey stick. If you were to, or a sock, I suppose it could be a sock lemma, but no, hockey stick lemma. One thing to notice, we showed that combinations come out as Pascal's triangle, and we didn't need we didn't need the factorial representation in order to get that. We could get there straight away just by this observation here. This is n choose. And I'm writing a big N and a small r just to make it obvious that from the big number of things you choose a smaller number of things. You also come across the notation n, r. Same deal. I prefer n choose r because this looks like a vector with two components which are n and r. So this doesn't look like anything else.